Hello, hello, OCAM. It is your funny, sexy tutor, Tommy, again speaking. So, today we're gonna do some reviews on some things we have learned. The use of malonic esters and the use of acetic esters. Okay, so let's do some recalling. If we have a ketone and we want to add an R chain to the alpha carbon of that ketone, how do we do? Mind you, this is the alpha carbon because it's the carbon right next to the carbonyl carbon. Okay? So if you're answering 1 LDA and 2 RX, X being a halogen, you are right. Because in the first step right here, you will turn your ketone into an enolate by pulling off that little hydrogen right here with your base. The LDA is a very specifically designed base to do that instead of attacking right here at the carbonyl carbon. And then step 2 is just simple SN2 where you have that enolate attacking the R and then the R getting added right here. No sweat, okay? Pretty simple. But as we move forward, we see that there is another way to do this because as you learned for the case of ketone, sometimes we have differently substituted ketone. So I say like this. So here you will have to do several different controls to give your resulting substituted ketone different products. Okay, so if you want to add your R group to the more substituted side, this case being the right side, you will have to do it at a pretty high temperature, something higher than 25, so at say 40 Celsius degrees, and then Rx. So that's when it's gonna go to the more substituted side, and that product is called the thermodynamic product, okay? But if you are going to perform the same reaction under low temperature, so as say like negative 78 Celsius, step 2 is just going to be Rx. You're going to have that chain being added instead onto the less substituted side. And this product is called kinetic, as in fast, quick. Because you have more H's available on the less substituted side, so it's quick. Does not require a lot of energy, but it's less stable. Okay, so those are the two conditions you have to take into consideration when you're doing the reaction this way. Okay, so we learned also of malonic ester, which looks like this. Okay, 2 cetyl bonded O and then 2 OET on the two sides. Very, very symmetrical kind of molecule. And acetic esters, which is just like your malonic ester, but it only has one side being the OAT and the other side is just a methyl group. Okay, so what we can do with these is that we can turn them into different things. The malonic ester will give you a substituted carboxylic acid. So it gives you the R group on one side and the other side being carboxylic acid. Okay, whereas for the case of acetoacetic esters, you can have a substituted ketone in the end. So that will be this. Okay, so how does this all work? Let's see. Let's dive into the case of acetoacetic esters first because it's more simple. Okay. So right here is when you have your acetoacetic ester. And I want to turn my acetoacetic ester into that thing in the end, with the R group added to the alpha carbon of it. What I'm going to do. Okay, so first we can open up that little site by using a dose of NaOAT, which is a base. Well, in this case, NaOAT is for sure going to attack this H right here instead of these H's on the alpha carbon, even though they are all on the alpha carbon, because these H's are much more actually acidic, because you know they are resonance stabilized by these two acetyl bonded O. So you will form an enolate by pulling off one of the H's on that alpha carbon located in between the two acetyl bonded O. And you know, as I say, resonance structure, it goes like this, it could go like that, or it could also go like that. So there are multiple ways to disperse your charge around the molecule, giving you a pretty stabilized structure. Okay, so now we have an enolate, and you know enolate likes to attack people. Okay, so that means you're gonna have the R group now being added to that site. So your R group being here, the R group of your choice, mind you. So tag like this and like this, just like an SN2 reaction, giving you a chain added right in between those two acetyl bonded O. So here's the thing, you want to reach here, but you see that you're having something in excess. Okay, and if you are able to point out that this ester is in excess, you're right. So how do we get rid of it? We cannot get rid of it as is. We have to turn it into something else before we can get rid of it. And the answer of that something else is a carboxylic acid, okay? So under the treatment of H3O+, your ester on the left side will be turned into a good-looking carboxylic acid ready to leave. How does it leave? It will leave under the condition of immense heat, okay? And the mechanism of that is going to be shown to you right now, but I'm going to just cut this off right here so that you only are left with this on the left, on the right side, and on the left side is just CO2. Decarboxylation is what they call this process. How's it gonna happen? Okay, so look. Let me drag down this whole thing right here so that you can observe whatever that was happening. Okay, so you see right here, we have this pretty looking beta keto carboxylic acid. So how did I get that name? On the beta carbon relative to this carbonyl carbon, we have a ketone, and this is a carboxylic acid, which is the main chain. So that's why we call it a beta keto carboxylic acid. Straightforward, right? So under immense heat, we will undergo this little rearrangement where you have your molecule spinning around that bond. So then you will have the OH facing up, being right next to your acetyl bonded O to the right. Oh, what am I drawing? Yep, I'm drawing the right thing. Just like that. CH3 is being right here, and the R is right here. Okay, so right here we have three separate arrows. Let's look at them. The first one would be the one going from this double bond up to this H to capture that H, okay? And the bond between this H and this O will go down over here, okay? And the bond between the C double bonded O of the carboxylic acid and the C will go back over here to this bond, okay? So several things are happening. One thing is that you are forming an enol out of whatever you just had in the beginning. And then the other side of it will break off to form you a carboxylic acid. And you can pause this video at this point to see how bonds are being broken and formed. Okay, so this is what you have. You have your product being in the enol form, and you can just rearrange it into the keto form with a dose of acid, which you don't have to show. So beta keto tautomerization is what they call it. And this is what you have in the end. Oh, I forgot to attach my R group to this side. So that's my R group. So yeah, that's what you have in the end, which is what you want. Okay, right here. Okay, so that was the case of acetoacetic esters. What about the malonic esters? Same thing, actually. So this time, NaOAT. Oh, and by the way, you don't have to use LDA anymore. You can just stop at NaOAT because you have very acidic H's over here. So LDA is not necessary. You don't need that strong of a base. So NaOAT will give you an enolate after step 1, where you strip off one H at that very carbon. Okay, step 2 is the addition of your R group, which you know happens via SN2, as we keep saying. Okay, and then you turn those two ETO groups into carboxylic acid, or OHs, using H3O plus. Okay, so now you have a diacid just looking like this. And the good thing about this thing is that they are highly symmetrical. As you see, these two sides look the same. So in our product, we only want one side of it. Okay, so we have to take off either this or this. So how do we do it? Heat. Rearrangement is going to happen, and this is what you end up with. While the other side just being CO2, which you don't have to show. Decarboxylation, as shown before. Okay. So that's how you achieve this carboxylic acid in the end. Okay, that was all. Let me know if you have any question. Bye-bye.